Welcome to CSGuitars, the science of loud. Valve amplifiers are still the most desirable sound in guitar music. Despite the thermionic valve, or vacuum tube if you prefer, being made pretty much obsolete way back in the 60s when solid-state transistors became readily available, valves have managed to cling on to their audio throne within the guitar amplifier industry and are proving as popular as ever. But how does valve amplifier technology work? I'm going to break down the circuit of a classic valve amplifier and step through each part of it so that you can no longer be too afraid to ask. Here I hold in my hand the circuit diagram to this valve amplifier, the Orange AD30, which celebrates its 20th anniversary this year, although the circuit reflects design which is much older than that. This was Orange's attempt at re-establishing their iconic sound, but with a build quality to match this century's manufacturing techniques. This makes it a perfect candidate for this discussion, as it's an all-valve amplifier taking inspiration from early valve amp design. This circuit is the basic skeleton upon which all valve amplifiers have been built since the 50s and 60s. But before we start to look at the amplifier, we should first address these. The valves. All valves operate on the principle of thermionic emission. A cathode is heated to a temperature hot enough that the electrons are provided the energy to escape their outermost energy levels, literally boiling them off of the cathode surface. At the other end of the valve, an anode held at high potential attracts electrons across vacuum, generating a large current. Rectifier valves are diodes. In fact, two diodes inside the same bottle, performing full wave rectification on an AC voltage. Adding a third electrode provides us with a valve that can amplify. In a basic triode valve, the small audio signal is applied to the control grid. This limits the larger current travelling through the valve, and the signal collected at the anode is a much larger version than what was applied to the control grid. Inside the AD30 we have four ECC83s, twin triode preamp valves, four EL84s, pentode power valves capable of delivering 15 watts in a push-pull pair. This amplifier has two pairs, giving a total output of 30 watts. And a GZ34 rectifier diode, because we all love that saggy bottom we get from high volume voltage sag. This is the amplifier circuit, and it can be split into 5 operational blocks which we will look at individually. The preamp, the phase splitter, the power amp, output transformer, and the power rectifier, where we will begin our examination. In conjunction with the diagram, you're going to see me go inside this amplifier, point out components, probe it for voltages, and perhaps even scope out some signal traces. So here comes my standard safety warning. The voltages, both AC and DC, found within a valve amplifier are dangerous. The voltages are high enough to deliver lethal current. The big capacitors can store lethal charge even after the amplifier is switched off and disconnected from the mains. So don't go poking around inside a valve amplifier unless you know what you're doing. Everything you're about to see is being performed by a trained professional, me, and I don't want you going replicating this at home. I'm not responsible for any electric shocks, injuries, or deaths that result from the stupidity of you ignoring this warning. Without properly designed power and rectification, a valve amplifier is not going to be able to do very much. The AD30 is running a range of voltages internally, ranging from the small 6.3 volts AC to run the valve heaters and indicator lamp, all the way up to 335 volts DC for the anodes of the power valves. The mains plug supplies 230 volts AC, or 110 volts if you're in America, to the amplifier's power transformer. This has many tappings which will step the voltage up or down for the requirements of different parts of the circuit. Transformers deal in only AC, but the valves require a constant high DC voltage in order to amplify, and that's where rectification comes in. The AD30 has one of these rectifier valves, a GZ34 thermionic diode, which converts the AC voltage into, well, not DC, but at least all the electricity is flowing in the same direction. Large filter capacitors then smooth out the ripples into a constant DC and supply it to the anodes of the valves at various different voltages. This is what we call the HT, or high tension line, tension being just another name for voltage, and amplifiers will quite often have an HT fuse or two in this line which will blow if anything goes wrong and the valves start to draw too much current. A very important safety feature. The standby switch manually disconnects the HT from the power valves, killing the amplification and silencing the amp. I labelled this entire section on the schematic as the preamp, but in reality what we have is two entirely independent preamps, one for each of the amplifier's channels. In the AD30, these two channels are close to being identical, with only a couple of component values different between them, but that's enough to get one of the channels to be brighter, distort harder, and sound more aggressive than the other. Let's follow the signal path. The guitar signal enters the amplifier at the input, where a 1 megaohm pull-down resistor sets the impedance of the circuit, ensuring that the signal is loaded correctly and won't incur losses right at the start. Now we can get into the preamp proper and hit the first of two gain stages, one half of the dual triode ECC83 preamp valve, which amplifies the signal. The resistors and capacitors that surround this triode set the amount of gain, control the valve's bias, and dictate its frequency response. We next hit the gain control, which is attenuating the signal coming from the first gain stage, dictating how much of that signal will reach into the circuit beyond. That goes straight into the second gain stage, the other half of the same ECC83 preamp valve, and more amplification is applied. This gives us a very simple two-stage cascading gain structure with an attenuation control in the middle, with the range to go from no signal to the full capacity of both gain stages flowing into one another. This is an incredibly simple preamp section that takes us from clean to thick classic rock distortion with just one preamp valve per channel. These single triode gain stages are the fundamental building blocks of all valve amplifiers. If you were to redesign the AD30 to give it more distortion, you could simply add more of these triode gain stages in a chain until your desired saturation level was reached. The AD30, like any amplifier, has a preamp section designed to deliver a certain sound, the components shaping the tonal characteristics of the signal as it travels through the gain stages. The EQ controls that sit at the end of all of this simply allow some tailoring of that hard selected sound, with each of the controls attenuating within different frequency ranges as dictated by the designer. The amplifier's sound will most likely have been designed using the midpoint values of those potentiometers, and the EQ controls allow some adjustability in either direction to factor in for using different guitars, cabinets, effects, and the room it's all being played in. These controls are very much there to assist the amplifier in sounding consistent regardless of what other equipment it's being used with, rather than a tool to drastically reshape the sound of the amplifier, as many misinterpret the EQ section to be. Now we can start to get into some of the interesting stuff. This is the phase splitter circuit, and it again utilises a twin triode ECC83, but it's not amplifying in the same manner as we saw with the other preamp valves. Yes, this part of the circuit will indeed make the signal louder, but its main job is to split the signal into two copies with opposite phase. The reason that it does this will become clear when we come to look at the power amplification section beyond. This stage is setting up to drive the power valves which operate in push-pull. The use of the low headroom ECC83 in the phase splitter allows a bit more distortion from the preamp. Fantastic for something like the AD30, which is all about distortion. A pin-compatible ECC81 or 82, which are cleaner, higher headroom versions of the 83, would be a better choice for an amplifier that's designed to stay clean, as it won't push as much grit into the power valves. A dual layer master volume control sits at the end, attenuating the level leading in to the power amp. While the preamp is there to apply gain and EQ, forming the sound of the amplifier, the power amp section is there to make that signal loud. Leading into the power amp section, we have two pairs of EL84 pentode valves, each half being delivered an identical but phase inverted copy of the preamp signal to their control grids. When one half of the valves conducts more, the other half of the valves conducts less, and when the signal voltage inverts, the valves swap their work. This is what we call a push-pull arrangement, with each pair of valves working together to amplify the signal. One half taking the brunt on the positive hemicycle, and the other half handling the bulk on the negative hemicycle. This push and pull delivers a more powerful and more efficient amplifier than if the valves were operating in a single-ended arrangement, where all of the valves were amplifying all of the signal all of the time. The power valves in the AD30 are cathode biased, meaning that 1, swapping the valves in this amplifier is very easy and I don't have to worry about performing a rebias, and 2, it affords a little bit of natural compression from the power section, but that is kind of dependent on what class of amplifier we're dealing with here. The marketing detail for the AD30 claims it's operating in Class A, a very linear, if inefficient, amplification method. However, there is no physical difference in the topology between Class A and Class AB, a distinctly more efficient amplification method, even if some of those desirable even order harmonics get cancelled in the process. It all depends on how the amplifier has been biased, whether it's operating in Class A, Class AB, or more realistically, a little bit of both depending on how hard the amplifier is being driven. Hello, future Colin here. I just want to add a little bit of further clarity to the Class A and Class AB thing that I was just talking about. Class A push-pull has the valves tuned in such a way that they conduct across the entire signal. They're still pushing and pulling, one valve working harder in the positive, the other valve working harder in the negative, but there's no point at which either of the valves shuts off completely. This is great for linearity and therefore fantastic for tone, but a lot of the power is wasted as heat, meaning it's not very efficient and it doesn't get good power to volume transfer. The flip side of that is Class B, where the valves are tuned to stop amplifying as soon as they cross over from positive to negative, or vice versa. This means that the valves are only amplifying 50% of the time, which is obviously more efficient, but you get this weird bit in the middle of the signal where no amplification is going on and it ruins the waveform with crossover distortion. The obvious solution is to tune the valves somewhere between these two extremes, having them amplify through crossover and then shut off some way into the opposite hemicycle. This is Class AB. It's literally Class A until it isn't and starts behaving as Class B. This means that below a certain signal volume, a Class AB amplifier is operating in Class A, and will only get out of that once the amplification has become enough to get over the Class A threshold into Class AB. The Orange AD30 might be tuned for Class A all of the time, or it might be tuned for Class A over most of its volume range and then changing into Class AB right at the top of its volume control, which would make sense if you want to maximize the power and efficiency through the amplifier. You get the best tone over the majority of the operating level and then the volume when you actually need it. I bring this up as there's a bit of a history of amplifiers calling themselves Class A when they're technically not. Class A is one hell of a marketing term, and if it's operating in Class A most of the time, is it really a lie? I don't know which the AD30 actually is, and honestly I don't think it matters as long as the amplifier sounds good, which it absolutely does, but it's just something to keep in mind. Unlike the preamp valves, which had fixed resistors as their anode loads, the plates of the power valves connect directly to each end of the primary coil of the output transformer. With 335 volts DC connected to the centre tap of the primary coil, the output transformer not only delivers high voltage to the anodes of the EL84s, but also forms the interface between the power amp and the speaker, practically acting to match the impedance. Impedance in audio systems needs to be matched between source and destination so there are no power or tonal losses in the transition, nor any damage to the circuit. It's the transformer's job to match the impedance between the speaker and the output valves. The secondary coil has tappings for both 16 ohm and 8 ohm speakers. Of course, impedance isn't a static value. It's frequency dependent and changes based on the frequency content of the signal being amplified. The output voltage rises to match the impedance of the speaker to maintain a consistent current, and it's this ever-evolving reactive interaction that gives valve amplifiers their signature feel, the sensation that they are part of the performance, reacting to what you play. It's also why having the correct load attached to your valve amplifier is incredibly important. The amplifier sees having no cabinet attached as an infinite impedance, which the output transformer will try to match by raising its output voltage to infinity, obviously burning itself out long before it can get there. Connecting a speaker with too high an impedance will have a lesser effect than not connecting a speaker at all, but it can still drive the voltage high enough to damage the amplifier, causing arcing within the transformer or screen grid failure in the power valves. Connecting a speaker with too low an impedance will cripple the amplifier's power output and force the valves into a cold bias state. Unlikely to cause any damage, but also unlikely to sound any good. All of the above culminates in a raw valve amplifier sound that will drive into distortion easily, has natural compression, has rich in harmonic content, and will sag out when driven hard. One that sounds a little bit like this. There is so much more detail I could go into with regards to the science and operation of valves and the amplifier designs that utilise them. These devices are magnificent, both simple to construct and difficult to understand at the same time. However, I hope that this brief autopsy of the AD30 has given you a deeper understanding of how valve amplifiers work and what parts they contain. If you fancy getting one of these amplifiers now that you've heard all about it, links will be in the description. Don't forget to click all the buttons you're supposed to make this video viable to the ever-changing whims of the YouTube algorithm. That's all for now. Keep it loud and stay safe. That there British guy says too damn funny.